So let's say two people are walking down the street and they bump into each other. So they'll just shake it off and walk on. Sometimes this happens with molecules too. They just bounce off each other and that's all. But what if these two people were to bump into each other and during that collision, one person's arm got severed and reattached into someone's head, and the other person without an arm? Now that sounds really weird, but this is similar to one of the many ways molecules can react with each other. Two molecules can join and become one. One can split apart and become two. Molecules can switch parts. All of these changes are chemical reactions. We see these happening everywhere, like when fireworks explode, like when iron rusts, milk goes bad, and like people growing old to young to dying and decomposing. But these chemical reactions don't just happen. Everything has to be right. So first, they gotta hit each other with the right orientation. And second, they need to have enough energy. Now, you're probably thinking that a reaction just happens in one direction and that's it. Sometimes that's true. Things can't be unburnt or unexplode, right? But most reactions can happen in forward and reverse. There's no reason that our face arm guy can't unbump into armless girl and become normal. Get to this point where more and more people end up with arms attached to their faces or arms missing, right? But as the number of people with arms and face missing arm grows, the collision between these people become more likely. And when they bump into each other, normal people appendages are reduced. Now the number of limb transfers per second will start high and then fall, and the number of limb transfers per second backward will start at 0 and then rise. Eventually they meet. Even though these people are still bumping into each other, they stop changing and exchanging limbs. We call this equilibrium. Some factors affecting equilibrium are enthalpy, entropy, concentration change, pressure, temperature, and catalyst. So let's say to this equation, we were to increase the concentration of CO. Okay? This will shift to the right, the equilibrium, because it will try to reduce the amount of concentration we added in the chemical equilibrium. Okay? So it will shift to the right if it was a concentration change. Now, let's say we change pressure. So we can see here, there is 1 mole, or 1 mole and 3 moles. That gives us 4 moles. And 2 moles on this side. So this applies only for gas. So if we change the pressure, equilibrium will shift to the right. Again, because there's 4 moles and 2 moles. Now, let's talk about temperature for a reaction product. So for a reaction in product, temperature will increase. So it'll be a positive temperature. We favor the reverse reaction to the left. Okay? And this would be endothermic. And if we were to decrease temperature, so that's decreased temperature, we favor forward reaction. That would be exothermic. That would go to the right. And one thing about catalysts is if we add the addition of a catalyst, it helps the equilibrium react or reach faster. So, and these examples of these factors and how it's affected is Le Chatelier's principle, where the system tries to maintain its equilibrium state by relieving its stresses by shifting. Let's talk about something we need to know, which is equilibrium constant. It's a number that expresses the relationship between the amount of products and reactants present at equilibrium. And it's in a reversible chemical reaction at a given temperature. Now its formula is K equilibrium K constant, we can call that, is products over reactants. And the temperature is also written as temperature affects KEQ. That is KEQ, and we'll say temperature, right? Now, if there is more products than reactants, then key EQ is greater than 1. Now, if there is less products than reactants, right, then key EQ is less than 1. Okay, so there's two theories we're going to talk about and two bad definitions that define acids and bases. An Arrhenius acid is a molecule that will donate a hydrogen ion or proton when dissolved in water. We call it a proton because it's a typical hydrogen atom and only has one proton and one electron. So if you make it a cation by removing the electron, all you have is a proton. Now an Arrhenius base is a molecule that will produce a hydroxide ion when dissolved in water. So the acid provides a proton and the base provides an hydroxide. However, this is only when dissolved in water. That's where the other definitions come in. Now, with the Bronsted-Lowry definition, we refer to what happens to these hydrogen ions, times of the hydrogen ion or proton. So the acid is a proton donor, like the Arrhenius acid, but the base is defined as a proton acceptor. So if there is a compound that will bond with a free proton, it is a Bronsted-Lowry base. And unlike Arrhenius acids and bases, this doesn't have to be in water. There are some common, well-known acids and bases. So here is HCl, CH3, COOH, also known as vinegar, NaOH, and citric acid, C6H8O7. Now, what you see common with these acids are most of them are colorless, and some of them have odors, and they also have these sour tastes. These are known as like acid or acid properties. And here I listed at least 4 properties of every single one. We can see HCl is colorless, corrosive, strong odor, and non-flammable gas. Vinegar is colorless, pungent smell, sour taste, and corrosive. NaOH is soluble, it's solid, odorless, and higher viscosity than water. Then we can see citric acid is odorless, colorless, acidic taste, and highly soluble. From the equation, which describes the behavior of acidic acid in water, could you identify the Bronsted-Lowry acid and the Bronsted-Lowry base? So, the Bronsted-Lowry acid is acetic acid because it releases a proton. Water is accepting a proton, which makes it a Bronsted-Lowry base. The acetate ion is formed when acetic acid releases a proton. The acetate ion is a conjugate pair in this reaction. The hydronium ion is formed when water accepts a proton from acetic acid. This is the conjugate acid in the reaction. When a Bronsted-Lowry acid releases a proton, the resulting species is a conjugate base. When a Bronsted-Lowry base accepts a proton, the resulting species is a conjugate acid. Acetic acid and acetate ion is a conjugate pair. So, can you identify the other conjugate pair? Well, water and a hydronium is the other conjugate pair. Let's consider a prototypical strong acid, hydrochloric acid. If we put hydrochloric acid in water, it dissociates into a proton and the chloride ion. Because it dissociates completely, we say that it's a strong acid. Now, what about sodium hydroxide? If we put sodium hydroxide in water and it also dissociates completely, we call it a strong base. Now, if we put ammonia in water, it only dissociates a little bit. Therefore, we say ammonia is a weak base. Now, let's say we give this question. Calculate the OH minus and the H plus of a 1.0 times 10 to the power negative 3 m solution of hydrofluoric acid, a strong acid. And another question, calculate the OH minus and the H plus of a 0.0020 m solution of CaO2, OH2, a strong base. Now, to solve these, we need to establish that the equilibrium constant for this reaction is called the ion product constant of water, liquid water, Kw, the constant of water, and is defined as H3O plus OH. We'll get to this later, okay? Now we can write out HF is equal to 1 times 10 to the power of negative 3 molar, and our H3O positive is also 1 times 10 to the power of negative 3 molar. And this is a constant of water. Constant of water is 1 times 10 to the power of negative 14. And we solve for OH. OH minus equals 1 times 10 to the power of negative 14 over H3O positive, which equals to 1.10 times 10 to the power of negative 14 over 1 times 10 to the power of negative 3, and that gives us 1 times 10 to the power of negative 11 molar. That is our answer. Now let's move on to the next question. Now we're trying to find the H plus. So now we know CaOH2 is it's a strong base, right? Now this is a forward and reverse reaction of Ca aqueous, I believe, 2 plus 2OH minus. Now we need to know this, okay? So now we know our OH minus is equal to 2 CaOH2 in bracket, which is equal to 2 multiplied by 0.00 molar, which is equal to 0.0040 molar. Now we can solve for our H. H plus is equal to 1, we need to know the K constant of water, obviously, times 10 to the power of negative 14 over 0.0040. And that gives us our final answer, 2.50 times 10 to the power of negative 12 molar. That is our answer. There's another method that we can use to measure the concentration called pH. pH has a simple definition. It's just the negative log of the H plus concentration. This is a useful way to measure the concentration of ions because it brings the numbers into something much closer to 1, and which is much easier to work with the values. If we use the concentrations that are given above, 1 to the power of 10 to the negative 3, 1 times 10 to the power of negative 7, 1 times 10 to the power of negative 9. If we put this into the equation, we get the following pH values: 3, 7, 9. And in an aqueous solution, a neutral system has a pH of 7. Any smaller than 7 is an acidic, and we will have a concentration of H plus that's larger than 10 to the minus 7. Any pH greater than 7 will be basic, and we'll have an H plus concentration smaller than 10 to the minus 7 molar. Now, pOH is a method measuring base concentration, and it works in exactly the same way. Water has a property called autoionization, where liquid water can split up into H plus and OH minus ions. This equilibrium has its own expression, pKw. There's no liquid water in that K express the position because liquid typically doesn't go into a K expression. The K value for this equilibrium is special. It's called Kw and has a value of 10 times 10 to the minus 4, like we said before in our last equation and word problem. And in any aqueous solution, whether it's acidic, basic, or neutral. So 10 to the 1 times 10 to the minus 14 is always constant. Now, water exists and water will exist in the equilibrium, so it means no matter how much acid or how much base you put in the system, water's expression will be true. So if you have an acid with a lot of H plus ions, you'll have very few OH minus ions, but their product will still equal 1 times 10 to the minus 14. And this means that in any solution, if you use the H plus ions concentration to calculate the OH minus concentrations and vice versa. It's also possible to write a pKw. Now, pKw is calculated the exact same way a pH or a pOH is calculated. The pKw is for pure water and is always 14. And if you take the negative log of our K expression and you take the negative log of both sides of the expression, you end up with the following. And this means for that any aqueous solution, you can say that the pKw is equal to the pH plus the pOH. Percent ionization is another useful tool that chemists use to find the extent of the reaction. Percent ionization shows us how much of the original compound dissolved in the solution to create ions. The extent of the reaction can also be found using an equilibrium expression. However, percent ionization quantifies as the amount of specific product compared to the specific amount of original reactant to find the percent ionization. All you have to do is divide the concentration of ion of interest by the original concentration of your reactant and multiply by 100. Let's look at an example. So, calculate the percentage of H3PO4 molecules ionized in a 0.10 molar H3PO4 solution. Now, we have all our values. I've already done some of this ahead of time, but we have our H3PO4, which is forward and reverse, H plus H2PO4, and we know that our K1 is equal to 7.5 times 10 to the power negative 3, and this is because if we have a polyprotic acid, the concentration of everything will be dictated by Ka1 since it's greater than Ka2 and Ka3. So let's fill in our ice table. So this will be X minus, X plus, X plus. And, oh, whoops. That's in the wrong spot. X minus, X plus, and that will be 0.1 minus X, X, and X. And now we can write it out as Ka is equal to X over X by 0.1 minus X is equal to 7.5 times 10 to the power of negative 3. Then we can rewrite it as, I'm running out of space here. X squared is equal to 7.5 times 10 to the power of negative 3 multiplied by 0.1 minus X squared plus 7.5 times 10 to the power of negative 3 X minus 7.5 times 10 to the negative 4 is equal to 0. And then we get our X value after we get X is equal to 0.024. You guys can plug it into your calculators, and which is equal to our H plus EQ. Now we gotta plug this into our original equation as above. So then we can say our X, or percentage ionization, is equal to H plus EQ over HA plus initial times 100. So we can say 0.024 divided by 0.10, which gives us, multiplied by 100, gives us 24. So we can make an assumption that larger Ka means larger percent ionization. Dissociation and ionization is a really simple topic, and I'll just explain it really quick. So bases dissociate in water, and acids ionize with water in the two-step process. Now we see that bases dissociate, NaOH with H2O, and it dissociates. Now here is a little different. First step is a dissociation, as you can see. Then the H ions ionize with water, create hydronium. And then the last step is ionization, which is what acids do. They ionize with water in the two-step process. You can see right here. If you're ever trying to find out what the pH of a salt solution is, break it up into its ions and see how each of the ions affect the pH of your solution. For example, let's talk about this. So NH4 to SO4 reacts to produce 2NH4 and plus SO4. We know this is acidic, and we know that this reacts to SO4 plus H, reacts with HSO4. Now, we know that H2SO4 is a very strong acid. So that makes this its weak conjugate base. So because of this, we know that this salt is very acidic solution. Let's look at another one. NH4CN produces NH4 plus CN. Now we are given the Ka of NH4, 5.8 times 10 to the power negative 10, Kb of CN, which is 1.6 times 10 to the negative 5. However, let's do what we did before. Let's use the CN. It's the conjugate of a weak acid, HCN, right? Now, instead of that, let's just look at these numbers. We can see that Kb is greater than Ka. So we can come to the conclusion that this salt is basic. Acid-base titration is a way of determining how much acid or base is present in solution by determining the precise volume of acid or base that will completely react with it. So, on a titration curve of an acidic solution, the pH is plotted against the volume of the base, and that's progressively added. And as we add base, the pH slowly rises, then sharply rises towards the equivalence point, which is right here. So you can see that it's at 7. Now, this is the point where it's precisely enough base that has been added to neutralize the exact amount of acid in solution. So when we perform titrations, we recognize the equivalence points by using something called an indicator. This is a substance that will turn a vivid color once the strong equivalence point has been reached. When we neutralize a strong acid with a strong base, the equivalence point will be 7. If either or both species are weak, this number will vary. Let's talk about an example. Now, 3 molar H2SO4 plus 2 milliliters of NaOH, and it takes 11.6 milliliters to reach equivalence point. Now, we need to convert this number, 11.6 multiplied by 1 liter over 1,000 milliliter equals 0.0116. liters. Now we use this value, 0.0116, multiplied by 3 moles over 1 liter, which is equal to 0.0348. Now this is our acid ratio. Then we use stoichiometric ratio. 0.0348 mole acid is equal to 0.0348 mole base. Now we can do this. 0.0348 mole base over 0.025 liters, which is equal to 1.39. That is our answer. So we can write that NaOH is equal to 1.39 moles per liter. And we arrive at the concentration of the reactant. Now we've come near our end. Now let's talk about buffers. A buffer is a solution that has an ability to resist change in pH when limited amounts of acid or base are added to it. Buffers are made by combining a weak acid with its conjugate base, or weak acid or base with its conjugate, obviously. Now, in such a solution, because of both acid and conjugate base are present, they are able to neutralize a small amount of any acid or base that are added in the solution. Now, chemical buffers, such as bicarbonate and ammonia, they help keep the blood's pH in a narrow range that is compatible with life, which is around 7.4 to 7.6. See, buffers are used everywhere around us. Hopefully this video helped you understand a little bit more about equilibrium and some of the calculations that I provided, as well as a little bit better of understanding of acids and bases. Thanks for watching. Have a good one.